We're probably close enough. Welcome back, everybody. So we're on our third exam week, and our third exam so far is covering up to sections 11.10. 11.10 is quite large, and we only just started it. So the actual exam questions that will come out of 11.10 won't be too over the top. It's going to be one of the basic type of questions you'll see that we're going to solve on the board today. So if you'd like further practice on that section 11.10, there's extra problems that you can find here on the Moodle website. Because this is a section that's going to be examined on Thursday, they're only for suggestion. So if you do want to hand them in for the sake of feedback, I'm happy to take them and look over them for you and return them later. But the one assignment that is going to be due on the Thursday of this coming week is assignment 11 at the moment. So it's just the two sections, 11.8 and 11.9. Before we get started, any questions folks have from those two sections in the homework or the reading? Okay, let's just dive in then. So the work we're going to do today is pretty similar to the kind of things that you have to do in 11.8, 11.9, except for the very start does feel a little bit different when we come up with the Taylor-Maclaurin series. But also just to mention for the exam that's this Thursday, keep in mind that we will be providing the series test flowchart. It is going to print as black and white, so that's kind of unfortunate. And there's a note that says, this will not be provided, so it won't give you a whole bunch of problems. That was just extra practice. If you want to look over those, I think I have partial solutions to some of these on what tests can be used. I tend to put a little bit more work on this document. So if you open this PDF, it goes back to the sequences and series flowchart, and it's just trying to identify what I thought, when I just eyeballed it, would look like a good test to use. I'm not completely happy with 38. So that's why it says try out the test for divergence. Let me know what happens on that one. I think 38 was meant to be kind of a nasty one in that set. And then the rest of them are saying possibly these tests will be used. I feel like I said use limit comparison test a lot on these. So whether or not those go through as intended, well, I'll have to find out when I do another pass on these problems. But other questions folks would like to discuss about the exam 3 coming up? I'm going for between 7 to 8. So if I go for possibly 6 to 8, let's say, if it's going to be 6 questions, it may be one question has 3 short parts of testing for convergence divergence. So if it's 6 questions, then there's possibly altogether really about 8 to 9. But actual problems you'll see on the exam, it's going to be anywhere between 6 to 8. Other questions about it that folks would like to discuss? Okay, so the problems are going all the way up to 11.10. If you look at the sample exam 3 problems, then this is essentially the scope of what could be asked on the exam. And if you look at the exam 3 given in 2017, then you'll see about what the real exam exactly what the real exam looked like. At the very bottom are some partial solutions. Some of them have complete solutions, step by step. So this will tell you about what to get into. Keep in mind that for the exam, it is a 3 by 5 inch note card of notes. Ignore this right here. This was 2 years ago, and back in the day, I mean, this sounds like a great deal, but that's all they got. So we are going to get an entire flow chart, which is amazing, and then you get the note card as well. So it is a better deal. Ignore this. That's just how it was printed, as in 2017. They didn't have the solutions either. That bit's extra. Other questions about the upcoming exam 3 then? Okay, so, oh, sorry, go ahead. Go ahead. I'm thinking about possibly doing that as a problem on the exam. So yeah, to give yourself some guidance on what could go as a decent question along those lines, take a look at, say, problem number 2 or problem number, let's see, there's problem number 2 at the very top. And problem number 2 is it. But that's also a feature that we'll look at in building the Taylor-Maclaurin series in this section. So I would say possibly you should expect something along these lines. But if I do put that on the exam, I want to make it kind of short, only because if I do go with this, I don't want people spending too much time coming up with a pattern for the nth term, since there's probably better things you could be showing to demonstrate your understanding. Other questions about that? Yes? Similar is kind of dangerous. If you did say, go to something that's very, very similar, it could possibly be partial credit, but that would have to be handled on a case-by-case basis because I would have to decide on things along the lines of if the similar problem has the same kind of core issue that was part of the exam question and things like that. So I would say that if maybe, for example, you just miscopied that there was n squared and you solved it as a different series, because that power 2 is really hard for me to read as well, then you would still possibly get partial credit for that. And possibly if it was just one tiny thing that caused a typo, but your problem was just as good, had the same objectives, then you may possibly get full credit, maybe minus 0.5 at worst. But again, it's a very, very kind of case-by-case kind of situation, sadly. But other questions about that? So I would say for the exam you get, it has to be essentially exactly this. If you make a change, essentially because of a typo or something like that, then it would be changing the question, and it would have to be handled essentially case by case, which is not the best answer. Sorry about that. Other questions or clarifications about that people have? Okay, so the actual exam is going to be about this long. This particular exam had, I believe, 7 questions, but one of the questions did have multiple parts. It had one part that was 3 parts altogether, where you're just testing for convergence divergence with 3 random series. So you could say it was really an 8-question or 9-question exam at the very end. But if there's any other questions, we'll start our work for today. Any questions folks would like to discuss? Since it is kind of a review week, I'm happy to go over any questions folks have, whether it's, say, homework, problems off the sample exam, or otherwise. But if not, let's carry on to section, say, 11.10, and do the problems like you'll see on the actual exam today. Or excuse me, after the exam Thursday, we'll do those problems today on the board. Any questions then before we give them a try? Okay, then let's start. So we're dealing with Taylor and Maclaurin series. Taylor and Maclaurin series are really the same kind of work that we've been doing in sections 11.8, 11.9, where 11.8 was all about a power series centered at A, and this was our core definition of what we meant. Power series centered at A is just something that looks like this, where x minus a to the n, this is the centered at A portion, and a variable raised to the power n is all we mean by power series. Then last class we did a pretty long derivation, but it was worthwhile since this is how the homework problems go anyways, for this theorem 5. It tells us if a function does have a power series representation, then in fact, this c sub n, the coefficients of the power series, is equal to f to the nth derivative, evaluated at the center, divided by the factorial, and this entire thing would be the power series representation of f. In this situation where we use this formula for c sub n, the coefficients, we would call this a Taylor series, if a is, say, 5. If a was 0, we'd call it the Maclaurin series. So it's really just more of the same similar kind of work that we've seen before. But the work to come up with the c sub n is really the same kind of work as problem number 2 on the sample exam, where we have to determine the pattern for an nth term. So that's the major fundamental work of this. Let's try with a brand new problem. The instructions for these kinds of problems are indicated in a special way to essentially tell us we're using theorem 5. The instructions would say, find the Taylor series representation of, let's let it be f of x equals the natural log of x centered at, let's say a is 1. That should be a decent one. Yeah, let's go with a is 1. So we want the Taylor series representation of the function, natural log x, at a is 1. And the problem then goes on to say, using the definition of Taylor series. It's kind of a weird way to say it because we're saying use the definition, but we're citing theorem 5. But really the punchline to theorem 5 is this formula in the box, and the definition is that we call it the Taylor series, Maclaurin series. So we're kind of wrapping this up together as a theorem / definition. And the problem says come up with a Taylor series using the definition. It means using this. So we're going to build the C sub n from very first principles and then throw it all into the box. But really the thing that's circled is the entirety of the work for this kind of problem, unless we add a little bit more. Let's add just a tiny bit more. The bit we're about to add is going to make this a horrible exam problem. It's just too long at this point, but it makes for a great review problem since this would be, say, a different question on the other exam or on the rest of the exam. It says then, find the radius of convergence. Just the radius, not the interval. But keep in mind, if it says find the interval of convergence, that is different and extra work as well. So this would be 2 exam problems altogether. First part is to find the Taylor series. Second part is to find whatever you produce, its radius of convergence. But in either case, this is how we're going to start. We do a 2-column system, where in the first column, we do f of x in row 1. Then amongst all the remaining rows that we produce, we'll be looking at higher and higher order derivatives. In the next column, we look at f, evaluate at the center, which was 1. Which becomes the natural logarithm of 1, which is 0 in this problem. So our whole objective with this second column is, this is our goal. If we can put down a formula for the nth derivative of f at the center 1, then notice that propagates the entire numerator of this formula. We just have to divide it by n factorial, and that goes exactly here, where the problem is completed. So really, this is what we're trying to hit. As soon as you have that formula, the problem is over, and it's just a matter of really copying. But with the first with the 0th derivative, you could say, we're starting at 0. We have f at 1 is 0, and there's no pattern to do here. So we need at least 3 lines. Sometimes we need possibly quite a bit more before we see the pattern emerging. So we just go on to row 2 very next. Any questions so far with what we've produced or what the goal is? Okay, so we're trying to get to here. To support that, we need to take, in row 2, the first derivative of f at x, which is 1 over x. And then in the opposite column, we do f prime at 1, which is just 1, and proceed from there. So far the pattern is 0, 1, and that's really just not enough for me to go anywhere beyond that to say what the nth derivative at the center should be. So we just keep adding more and more rows. Any questions so far? Okay, so just for the sake of convenience, I'm going to rewrite this as x to the power -1, so that when we go to the third derivative, we're just going to use the power rule and not have to worry about any issues with exponents. So next derivative, f double prime at x, will be the old derivative. We copy down the coefficient of -1 times x to a new coefficient of 1 less. So now we have negative x to the power of -2, and we have to evaluate f double prime at 1, which becomes really just -1. So it's not too exciting. So we go 0, 1, -1, and still that's not enough for me to really come up with a pattern. So we need a new row. And this can possibly go on for a little bit down the line. If you're doing this as an exam problem, at least give 3 rows before you go to the end answer, just as to say that's the part of the work to get to the nth derivative at the center. But questions so far with the third row? Okay, then we just repeat. We're off to the fourth row where we do the third derivative, f triple prime at x. Then the new coefficient of -2 from the last list becomes +2, -1 times +2, times x to the power of -3, which means the third derivative at 1 should be +2. So now it seems like maybe there's a pattern emerging. We went 0, 1, -1, +2. If you can say what the fourth derivative is at the center of 1, then we may just have it. Any predictions on what the fourth derivative should be at the center 1 without computing the fourth derivative? Not quite. You're close. It turns out it is negative. It ought to be -6, yeah. Or you could say -3 factorial, which is the same as -6. Does that make sense so far? it looks like, and a very common feature with these kind of problems, factorials are emerging some way, somehow. So if we go to the fourth derivative, just to check, at x, this would be -3 times 2 times x to the power of -4. And that's what produces the 3 factorial. If we did another derivative, we'll get a 4 factorial, but it would come out as positive next, because we'll have -3 times -4. So it looks like we can say, as a prediction, the fifth derivative at 1, it should go to, say, positive, and it's not going to be 5 factorial, it'll be 1 less, a 4 factorial. So it looks like that's the pattern that's continuing on, but we just have to check this list twice. It should be a pattern we believe carries going down, and a pattern that carries going up. So let's see how far up we can go. Right, questions so far with the factorials? Okay, before we get too far, let's recall some important facts about factorial functions. So we have 2 interesting evaluations for factorials. 1 factorial is always 1, or if you did 3 factorial, it means 3 times 2 times 1. But we allow 1 factorial to be 1 to establish a pattern. However, what do we say 0 factorial should be by convention? It's 1 as well. So if we allow 0 factorial to be 1, then we can go up to possibly here. So let's rewrite these. We have the fifth derivative at the center is 4 factorial. Fourth derivative is -3 factorial. Third derivative is positive 2 factorial. Because 2 is equal to 2 times 1, that's also 2 factorial. Then the second derivative is -1 factorial. Because 1 factorial is 1, so this still produces -1. This one is 0 factorial by convention, and this one has no pattern. This is a combo or pattern breaking event. So the pattern broke here. That's okay because it was the very first term. That very first term was 0. And if a pattern breaks in this specific way, then this is what people would end up doing. Re-index these. We should start at the first non-zero term, which was a 1 for f prime at the center 1 itself. But any questions so far? Okay, so we can allow this to correspond when we say re-indexing. We're going to allow this one to correspond to n is 0. This is going to correspond to 1. This will be 2, 3, and this is the nth derivative, where we now need a pattern. So we can say that the nth derivative, remember we're starting off at 0 because we're also re-indexing. It's alternating. We have positive, negative, positive, negative, positive. So we need -1 to a power of just n itself would do the job. Because if we let n start at 0, -1 to the power 0 will be positive. And our very first term was positive right here. Remember, we're deleting this one because it not only broke the pattern, which was offensive, but it's also 0. So there's no cause for starting at a 0 term. Then we need to put in something extra. We have factorials, but notice how the fourth derivative involves 3 factorial. So the nth derivative should involve n minus 1 factorial altogether. And that was our formula for the nth derivative at the center, fn at 1. Any questions about that so far?
Why is it n minus 1?
Mainly because of the pattern we see here with, say, second derivative involves a 1 factorial, third derivative involves a 2 factorial, which means the nth derivative should be 1 less factorial, matching the pattern that we saw in our list. It also had to do with the re-indexing and also the starting at 0. So we could start at 1 if we'd really like, but it's no harm done, just a different way to write the answer. The book would more likely than not just re-index it. Well, other questions so far to this step? Okay, so we have met our goal. We're going to start at 0, and this is going to be our pattern for the fn at 1. This implies then that c sub n at the center of 1 is always fn at 1 divided by n factorial. But fn at 1 is -1 to the power of n times n minus 1 factorial, which means we can expect a reduction here. When we divide by n factorial, Another interesting facts about factorials is that in factorial is also equal to n times n minus 1 times n minus 2 all the way down to 3 times 2 times 1. But if you put a factorial on it, then that's a decent way to do it as well. You could say n times n minus 1 factorial is n factorial. Does that make sense so far, however? Okay, so factorials are algebraically pretty malleable. One reason to do this kind of factorization with the factorial is because of the n minus 1 factorial that's already there. So n factorial can be thought of as n times n minus 1 factorial, which means there are no longer factorials, and we get negative 1 to the power of n divided by n. But if you look at that really, really carefully, if we put a series on that, then that's the alternating harmonic series, which is kind of interesting. So the coefficients for the natural log of n in a power series is the terms from the alternating harmonic. Kind of cool in a way. But remember, our goal was to come up with C sub n, which we just found through our tabular system, which allows us to write down this as the punchline. So by all this work, we have the following conclusion. So the natural log of 1, this is the Taylor series centered at a is 1, which means you probably want to do our approximation nearby 1. It's equal to the summation as n goes from 0 to infinity, and answers do vary because reindexing is an arbitrary choice. If you did start at 1, then that's okay. Your answer is going to look different, but if we reindex our series to the same starting value, it'd be the same thing. So we put in negative 1 to the power of n, coming from here, divided by just n, and we multiply that by x minus the center to the power of n. So this is natural log of not 1, but x. Sorry about that. So the function natural log x, as a Taylor series centered at 1, is exactly that. Any questions about that process so far? Okay, just a quick blurb then on kind of one important purpose of all this is the application of numerical analysis. You could say that this thing right here, it is an infinite sequence. So if I just want to approximate the natural logarithm of x using the Taylor series, we can do that approximation by only doing finitely many terms. Maybe say the first 2 terms. We start out at 0, plugging 0 here would be a problem. Uh-oh, that would be division by 0. We have a big, big problem. We canceled n minus 1 factorial. That left us with just an n down below. It cannot start at 0, however. Uh-oh, we should probably just allow this to start at, say, a 1. So this was our 0 term. Let's start this at n is 1, 2, 3, 4, and 5. So if we do that, that starting at 0 is a problem. We can start off at a 1 and go from there. I believe that fixes it. Does that look all right to folks so far? Not too happy about that last portion. Let me take a look at the fn at 1. So if we plug in and start this at 1, then this would have to be a plus 1 down the line to work out correctly. Since if we plug in a 1 right here, we need to have a positive term. So this will become squared at 1. Then this will be 0 factorial, which does give the 1. At 2, we'd have negative 1 cubed, so that comes out correctly as negative. And if we do 2 minus 1, that'd be 1 factorial. So yeah, I think it looks good. The reindexing was the problem. We should have called that just a 1 and kept it that way. So that's not necessarily reindexing. We're going to start the indexing at 1 itself. So start here. Since the first term itself was a 0 term, which was not a necessary contribution. Any questions about that so far? So that's a very helpful thing. It's always good to look again at your power series, see if it makes sense, see if you have avoid all divisions by 0 to see if you're on the right track. Then if we took finitely made terms starting at 1, we also have a plus 1 here, put that change in yellow. Then we would have positive 1, and this to the power of 1 would just be an x minus 1. So this is approximately equal to x minus 1 on the first term. Then when we go to n is 2, we get negative. We'll have 1 over 2 x minus 1 squared. That'll be positive 1 over 3 x minus 1 cubed, and then so on. Let's just keep it right there. So this is the end. This is the Taylor series. But if we want to approximate that Taylor series with just, say, 3 terms, this is what you could put in there. And if you really want to do something along the lines of evaluate the natural log of point, let's say 993, then this is a horrible problem to do. There's various ways to do that. One way is to just throw this into the calculator, and the calculator does it lickety-split. But the calculator is, in fact, doing this kind of stuff. They're using a lot more terms. We just put down 3. The calculator is taking your logarithm. 0.993 is close to a center of 1, so it's producing the Taylor series representation of your function at that center and putting in sufficiently many terms, so if you output 6 decimal places, it would be accurate to 6 decimal places. So all of that kind of stuff is happening behind the scenes in just a cheap $12 calculator from Walmart. It's kind of crazy. And that's one important value to this kind of work. Any questions so far with all that? Okay, so now we have a Taylor series for the natural logarithm, and the next portion again is kind of a review problem. It is an exam question in its own right, so I think it's a decent question to do next. It says, we now know that if the natural logarithm has a power series representation at 1, it would be this. This is our Taylor series. In fact, does have that. And the second part says, then find the radius of convergence for that power series. So let's do that very next. Any questions before we give it a try? Okay, so we're off to this portion, find the radius of convergence. If the problem says find the interval of convergence, keep in mind that is different kind of work. So it's always good to keep in your mind separate the radius versus interval. Radius just requires less work, and if we have a power series and we want to find the radius of convergence, then we'll just use the ratio test. More likely than not, that'd be a good idea, unless something in this format screams at you geometric series test. That's impossible because n is not as an exponent down here, so we'll go to the ratio test. So we'll say by the ratio test, r is going to be equal to, and let's fill that in once we complete this. The work below is that we have to take the limit as n goes off to infinity of the n plus 1 term divided by the nth term, which we call a sub n. But a sub n is exactly all of this inside this series. So at the n plus 1th term, we would get that this is limit as n goes to infinity, absolute value of -1 to the power of n plus 2. I mean, this all gets wiped out in the end through absolute values, but that's how it would carry in. Then it'll be x minus 1 to the power of n plus 1 divided by n plus 1. So that's our a n plus 1 term, and then the typical pattern is we take this, multiply by the reciprocal of a sub n, which is in that yellow box. But any questions so far with what we've written? Okay, should feel like a kind of a typical pattern of attack. Does it feel kind of familiar so far? Okay, so if you have just some random power series, and this one is less random, that's the natural logarithm of x, centered at 1, still the ratio test is a great way to approach it. And divided by a sub n means we'll put in n, -1 to the power of n plus 1, times x minus 1 to the power of n. Then the next work is to just cancel everything that survives and take the limit on the survivors. So we have the n plus 1th power cancels completely with x minus 1 to the power of n from the denominator. Then absolute value bars center around x minus 1. So we have x minus 1 in absolute values, but that is now a constant with respect to the limit as n goes to infinity. So we can factor out entirely and say it's x minus 1 in absolute value multiplied by the limit as n goes to infinity of all the rest of the cancellations. So anything with -1 to a power is also gone. Only survivors are n divided by n plus 1, but this is a very, very common limit. This has a horizontal asymptote exactly with the equation y equals 1, which means in the limit it's equal to 1 itself. So we have absolute value of x minus 1 times 1, which is the absolute value of x minus 1, and convergence occurs specifically when it's less than 1 in absolute value. But keep in mind, this doesn't necessarily tell us the radius right here. If we had, say, the whole thing divided by 5, then the radius would have been 5. If it was absolute value of 3x minus 1, then the radius is going to be something else, not necessarily a third. We'd have to do some algebra to work all that out. But if you have a coefficient of 1 in front of the absolute values, no division, coefficient run in front of x, then the less than 1 is, in fact, the radius. So we can say the radius is 1. That's a shortcut, though. Really the best way to see that the radius must be 1 is you would find the interval of convergence, figure out its length, and cut it in half. So let's maybe see what that would possibly look like, just as extra work validation. So if you have the absolute value of x minus 1 is less than 1, that would imply that negative 1 is less than x minus 1, which is less than positive 1. So this would be the same inequality, but without absolute values. We can add 1 to all sides to say 0 is less than x, which is less than 2, which means this is our picture so far. At 0, we have to test for convergence divergence. At 2, we do as well. But inside, we have convergence for sure. And we always had convergence at the center of 1. That tells us the radius itself must be 1. And we could just stop right there. If the problem says, find the interval of convergence, we actually have to test whether we converge at x is 0 or whether or not we converge when x is 2. But if it just says find the radius of convergence, you just need to state that radius and maybe do a little bit of extra work to see if that really comes out correctly. But questions so far with this kind of problem? So now we know how to represent the natural logarithm function. Let's try this all again with, how about sine? Let's find a Taylor series representation of sine. Let's make it a Maclaurin series and have it centered at exactly 0 for our next portion. Any questions at all so far? Okay, so let's repeat. Maybe not the entire full problem, just the first part. With the new function f of x, using the definition of, let's change this to Maclaurin series, since we'll have a different center. So we want to find the Taylor series representation of f of x. Let's let this be f of x equals the sine function, just sine x, using the definition of Maclaurin series. But when it says use the definition, that means we're building from scratch the coefficients c sub n, which means, once again, this is our major goal, to come up with the nth derivative at 0, the center. So let's wipe out these two lists and start from scratch. With the new function f of x, which will go there, and that function evaluated at 0. So because of the Maclaurin series, forgot to fill this out, the center A itself has to be 0. And f of x is sine x to start us off, which means f at 0 is, well, sine of 0, which comes out as a 0. So we have kind of the same sort of list to start us off, which means we can start our list at n is equal to 1, possibly, so far. Now we go to take derivatives until we find a pattern. So the derivative of sine becomes cosine x, and we have to evaluate that at the center of 0. What would cosine at 0 come out as? So we have 0 to 1, and so far so good. Then remember, we're only going as far as necessary to establish a pattern for this thing. We'd like to know what the nth derivative at the center is 0 would be equal to. So far we have 0, 1. That's really horrible for a pattern, which means we'll go to the second derivative. F double prime at x is equal to negative sine of x. And sine of 0 is still 0. So we have the second derivative at 0 is also 0. So we kind of sometimes think of this as the 0th derivative. It'll be the index n is 0 when we think of this as an ordered index. We think of this as the second derivative. And so far, the pattern is, it looks like at everything even, we have 0. So let's see if that continues to carry on by going to the third derivative. That would be negative cosine x. So what would the third derivative at 0 be?
-1.
Yeah, so we now get cosine 0 is still 1, but now we have a negative. And this is our pattern. We are going 0, 1, 0, negative 1. How do you folks feel about this list? Do you feel like it should replicate? Yeah, the next one is going to be derivative of negative cosine x is sine x. So let's maybe let this be our last derivative. So this is positive sine x. Since the derivative of cosine is negative sine, so we have double negatives canceling. So now f4 at 0 is still sine 0, which is 0. Then let's see if we have the pattern down by going to f5 at 0. Anyone see what f5 at 0 ought to be so far? Will it be a positive or a negative 1? Yeah, it ought to be positive. So that means we just about have this list, but our trouble now is the list has every other problem or every other term going to 0 for the derivative. So we need to re-index all of that. And to get a start, we have the following issue. We have that 2n is even for all n. So pick any integer n, and it is, say, 0, 1, 2, 3, 4, 5. 2 to the n is always even for all n. And f at 2n at 0 is always 0. So pick any n whatsoever. If n is, say, 3, we didn't go that far. If n is 2, then we'll be looking at the fourth derivative at 0, and it's always 0. That means the evens have effectively always died out because that is the numerator right exactly here. So we do not need any of the even terms. We'll go to only the odds and just the odds. So we can say for 2n plus 1 is odd for every integer n, and f at, remember I don't want to do f at 2n, we just want only the odds. So we do f at 2n plus 1 at 0, and this is the thing that we need a formula for right exactly there. Does that make sense so far? Okay, so all my odds go with first derivative, third derivative, and fifth derivative. So really our pattern is involving this, this, and this, and everything that has a 0 is just a distraction. So the first thing I notice is that we alternate. Is there anything else going on there? Or is it just an alternation? Will folks agree it looks like it's just alternating and that's it? Yeah, I agree. If all we see is negative ones, positive ones, then it really just comes down to this. Negative 1 to the power of n. We do have to get the power of n right. So now we have to imagine how would this work as if we were testing for the nth term in a sequence or a series. We just need to make sure these come out right. So if n is equal to, let's say, 0, we'd be looking at f to the power, or excuse me, the derivative of first derivative when n is 0. So this becomes, I'll leave it this way, 1, just to establish what we were trying to say here as a pattern was for derivatives. F at 1 at 0, that takes me to this because we've already done it. It comes out to a 1. And if we plug 0 here, that comes out to a positive 1 as well. So let's just try, say, the next two. If n is 1, we're plugging in 1 right here. We'll be looking at the third derivative at 0. And that should be a negative 1 by the formula. Going here, that's precisely what we had, a negative 1. So at this stage, I'd be pretty happy that the pattern looks correct. Let's just eyeball when n is 2. If we put 2 here, that'd be the fifth derivative we'd be looking at. 2 here squares it for a positive 1. And that's the fifth derivative at the center of 0 evaluated to a positive 1. So it looks like we do have the pattern down right here. Just put a little check on it. I don't want to box it because it's definitely not the answer, but it's most of the work so far. Any questions then to that step of getting f at 2n plus 1? Okay, so then we can't do Cn because remember Cn can be broken up into two things. It can be broken up as C2n, which is f at the 2nth derivative at 0, which is 0 divided by 2n factorial, but that's always 0. So we do not deal with c sub 2n whatsoever. We want to do the coefficients c at 2n plus 1 because that would be odd. So if we have f at 2n plus 1, that means you need a c at 2n plus 1, which would be this entire thing, negative 1 to the power of n, divided by 2n plus 1 factorial. So this should always match up to the 2n plus 1 we see down below there. Any questions so far? How do folks feel about this one to this step? I feel like this is maybe a very, very tricky one with every other term going to 0 in this series. Does this look all right to folks so far, to that step? Okay, so if we're happy about this, then we can come back over here and say, for the solution to the whole process, sine of x is now equal to the summation as n goes from 0 to infinity of negative 1 to power n. Really, we're just copying at this stage. Divide by 2n plus 1 factorial times, really we'd go x minus a, where a is the center, but the center is 0 in this problem, so we just do x to the power of 2n plus 1. And this is what makes it a Maclaurin series. There's no x minus a, just x minus 0, really. That gets simplified to that. Any questions so far with our solution for sine? Okay, so now we have a Maclaurin series representation for sine x. And this has a radius of convergence equals to infinity. We've actually seen a couple so far. Let's state a couple more. We've also seen that e to the x is a summation as n goes from 0 to infinity. Maybe I should box this one at this point, since this is the answer to the original question, and this is just extra Maclaurin series that we've seen so far. We weren't asked for the radius of this problem. It's just being stated for completeness. So e to the x is Maclaurin series. We showed that becomes x to the n times n factorial. This also has a radius of convergence, which is infinity. And another really important Maclaurin series that we've seen is 1 over 1 minus x. By the geometric series test, this is also summation as n goes from 0 to infinity of x to the power of n. And this holds precisely when the absolute value of x is less than 1. And those are the three Maclaurin series we've seen to date. So if we had one for sine, we should do one for cosine very next. Any questions first with those first three we've done? Okay, so next one is cosine of x. This, by the very same kind of steps, can be shown to be the summation as n goes from 0 to infinity of, this one's also negative 1 to the power of n. But keep in mind, if you dig deep in trigonometry, from trigonometry we're told that cosine is an even function and that sine is an odd function. We have 2n plus 1 inside here for the odd function. That's a great way to memorize this. For the even function, we use 2n, which is always even, x to the 2n, and that's the exact correct form. And it has the radius of convergence, r is equal to infinity as well. We like these whenever we can get them. We can't always get them. This diverges for all other value of x. But the radius of convergence being infinity tells us that whether you're thinking of cosine in the unit circle trigonometry definition, or if you're thinking of this power series, they are in fact one and the same. There's no approximation provided you're actually summing to infinitely many terms. So that's very, very helpful. But other questions so far with those Maclaurin series? Okay, I guess I have questions for folks so far then. Maybe we could do one more that kind of goes like this, where we come up with the actual Taylor series or Maclaurin series like we did here, or we could do an application next. So I'll leave it up to folks. Should we do an application or maybe one more for practice? Anyone for application? One person for application? Awesome. Anyone for practice like this? One more? Sorry, Christian, you got overruled. I'll let you have the veto power next problem. How's that sound? Okay, so let's maybe do one more practice problem like this. And these are the kind of questions you're going to actually see on the exam. It may be not something that's alternating like this because I feel like it's kind of tricky. Let's do one that might be more routine, that you would see as an actual exam question. So say, find the Taylor series representation centered at something using the definition of Taylor series once again. And this one is going to be f of x equals e to the negative 5x, and we want this Taylor series to be centered at a is equal to, let's let it be 1, just for the sake of convenience, so the algebra doesn't get too out of hand. So I feel like this as an exam problem would be a pretty decent one. It's not too long. If you know the method of how to get through it, it's not too tedious to get through. And if this is all you produce, just getting started, a table of derivatives, a table of evaluations at the center, and you didn't get any further, I would say that this is really possibly just half the credit because it is, in some sense, a good amount of the work. Depending on who you ask, that could be considered half the work right there, is to come up with this list. Then there's extra points going to be assigned for getting the formula for f sub n at the center and so on. Let's first start off with our brand new list. So f of x this time is equal to e to the power of negative 5x. We evaluate at the center, which is this time at 1. I guess it's been 1 for a while. So if we evaluate e to the negative 5x when x is 1, we'll get e to the power of negative 5. So that's a start. Now we go off to the derivative for f prime. So f prime at x, what would that be equal to altogether? Any volunteers for a good old chain rule derivative? I'll go first. I'll start it. So this one, if I was going to do a derivative of this, I'd do the derivative of the outer function, which is the base c exponential. So it would always look about like this, or parentheses around this, just for emphasis by the chain rule. What's the extra bit we'd have to throw in through the chain rule?
Negative 1/5.
Close. You're thinking of integration. Sorry, say again?
Negative 5.
Yeah, with differentiation, it would be a negative 5 altogether. So we take the derivative of the base e exponential, but then we multiply it by the derivative of what's in the parentheses, negative 5x, which produces that negative 5. So we have the derivative is equal to all that. That means f prime at 1 is now equal to, we're throwing a 1 here, so it's negative 5, e to the power of negative 5 still. And we're kind of on our way. At this stage, people might see what the pattern ought to be, but you should give me at least 3 rows for full credit for showing your work, say. So the third row, f double prime at x, will be equal to, and this is another kind of strange and common feature about these sort of problems, you don't want to simplify too much. By that I mean, if I did this derivative again, I would say it's base e to the power of negative 5x. The chain rule says multiply by negative 5 again into the already present negative 5. And I would cancel the negatives to make it positive, but I would probably leave it as a 5 squared. The 5 squared is more valuable to us as pattern seekers in this problem than a positive 25 is. Because a positive 25, it just doesn't show the same kind of structure that we're actually looking for when we're trying to produce this thing. We want to know the nth derivative of f at the center of 1. But if we leave it like this, we can now say the second derivative at 1 is 5 squared, e to the negative 5. And these things seem like they're starting to line up. Second derivative is tied in with the power of 2 on the 5. First derivative is tied in with the power of 1. And there's really a power of 0 on this 5, since 5 to the power 0 is also that hidden 1 that's also present there. So let's now see if we are on the right track. If we did the third derivative, another feature we see is that it's alternating, positive, negative, positive. So I'd say this next one ought to be negative. The power of 5, if we maintain the power, it went 2, 1, 0. So for third derivative, it should be cubed. And it looks like e negative 5 is just a feature in this problem. It's going to carry down all the way through. So if you can do this without referring to the derivative, then you may have the pattern down. Let's do the derivative anyways to see if we got it right. Third derivative of x will be 5 squared times negative 5, so that's negative 5 cubed, e to the negative 5x. And yeah, if we throw in a 1 there, that's what we would get. 5 to the power 3 negative times e to the negative 5. So I think we're ready for, I guess it's not a fraction. It usually is a fraction. But this time we're ready for the nth derivative evaluated at 1. Anyone see what the formula should be so far? It is alternating. Would you folks agree? So alternating things should start off with a negative 1 to a power. Recall, though, we're starting at an index of n is 0. This is an index of n is 1. So if we start off at 0, negative 1 to the power 0 would give us positive, and that's what we want. We have something that's positive there. What would you say the next factor should be? We've got the alternating part. What about the 5 to a power part? What would folks copy here for this portion? I didn't mean to get the negative there. Just the 5 to a power part.
5 to the n?
Yeah, it looks like this time the power on 5 lines up exactly with the derivative. So we'll just go 5 to the n. Then there's an e negative 5 on every single factor. It does have to be there, but it does not depend on n. We'll just throw it in. So we have the nth derivative centered at 1. What that then allows us to do is we'll plug in the formula for the coefficient, c sub n. So now we have that c sub n is equal to f of n at 1 divided by n factorial. But we have a formula for the nth derivative at the center 1. So this becomes negative 1 to the power of n, 5 to the power of n, e to the power of negative 5, all divided by n factorial. So that's the coefficients of the power series c sub n. Any questions at that step so far? Okay, so assuming that this was a 10-point question, I'd probably give, say, altogether 5 points for producing work like this, because that tells me you know how the process should go for producing the power series for Taylor or Maclaurin through the definition. Coming up with this, I'd probably call this, say, maybe 2 points to 3 points. Let's go with 2 points. I might call this maybe 1 point. So the whole thing getting c sub n is 3 points altogether. And then for the final 2 points, this is really just to summarize, to say all of this work has now shown, particularly the bottom line down here, that the original function, e to the negative 5x, is now the summation as n goes from 0 to infinity of, we grab all that stuff, negative 1 to the power of n, 5 to the power of n, e to the power of negative 5, divided by n factorial, and we have to multiply it by x minus a, but a was 1, to the power of n. So I'd call that 2 points to summarize by saying this function is in fact equal to this as its Taylor series. And that Taylor series representation turns out to be r is infinity once again. Any questions with that process so far? Okay, so this looks like a lot of stuff, but really the major work is really here, coming up with this 2 columns where the second column is really the column that we pay attention to. And it is that uncomfortable situation of we have to come up with a formula for the nth coefficient, which is like coming up with a formula for the nth term of a series or the nth term of a sequence. It is kind of tricky work, but it's something to practice. Now let's see how much time we have. How about one slightly different kind of problem, and then we'll call it a day. Does that sound all right to folks? Okay, so this is now a bit of an application to the Taylor series and Maclaurin series. It's also a good problem to compare and contrast why these last problems kept saying, using the definition, we were trying to obtain a power series. This problem is now going to say, given that, summation as n goes from 0 to infinity, x to the power of n divided by n factorial is the Maclaurin series f of x equals e to the x, find an antiderivative of, let's let it be e to the x cubed using power series. I think that's a good clarification there, because you could always use the fundamental theorem of calculus part 1, and that would be a bona fide antiderivative. We want a different kind of antiderivative using the results that we've been working up so far in terms of power series. So this is our solution. We want to solve antiderivative of e to the x cubed dx. We're not going to get a closed form solution to this, and the author's book says it's in fact impossible. There is no one function whose antiderivative in closed form is equal to e to the x cubed. But if we use power series, it's not going to be what we mean by a closed form answer. We do get an answer, so we're going to do that next. So this is just an assertion of what we're trying to get. All we're knowing is that this is the Maclaurin series for e to the x. So we know that e to the x is equal to the summation as n goes from 0 to infinity of x to the n divided by n factorial. And the radius of convergence for this thing is infinity. That's just extra information. So this is the interesting thing we can do. If we go back to section 11.8, which seems like a really long time ago already, we used a geometric series to rewrite different functions in terms of that geometric series. Now we can do the same thing. We can say then e to the power of x cubed. The x cubed is now playing the role of this x right here. It would be equal to the summation as n goes from 0 to infinity of x cubed to the power of n divided by n factorial. So all I've done is I've used a known Maclaurin series for e to the x. The statement of the problem would just tell you that that is the known series, so you don't have to derive it. That'd be way too much work. But this series is going to hold, or this formula is going to hold for any value of x. And in particular, with the radius being infinity, changing it to x cubed is not going to change the radius or interval of convergence. All we're doing is putting x cubed here and then working it out. So the Maclaurin series for e to the x cubed is the summation as n goes from 0 to infinity of x to the 3n divided by n factorial. So that's a very, very rapid way to get a power series. You just use a known power series formula, this one that was given. We could have done it with this problem, but part of the goal of this problem was just to see if we know how to build our Taylor series, and that's where this comes in. If the problem says on the exam, use the definition of Taylor-Maclaurin series to produce this Maclaurin series right here, we really have to go through this two-column system. But if the instructions say to do something else, like find an antiderivative, and they give us this information, then we can just run with it. We now have a Maclaurin series representation of e to the x cubed immediately in essentially one step, 2 steps if we simplify. And that's inappropriate unless it said, find this using the definition of Maclaurin series. Any questions to that step so far? Okay, so we have a Maclaurin series representation of e to the x cubed. That means we can go back to our goal. We want to find the antiderivative of e to the x cubed. So we say antiderivative e to the x cubed with respect to x is equal to the antiderivative of the summation as n goes from 0 to infinity, x to the power of 3n divided by n factorial dx. So all I've done is a substitution for the Maclaurin series of e to the x cubed. It goes exactly here. And now we have a really, really big and powerful theorem from section 11.9, which says, although there are infinitely many terms, this has a positive radius of convergence. It's in fact infinite. So we can integrate infinitely many terms in one shot. This would then be equal to the summation as n goes from 0 to infinity of, when we integrate infinitely many terms with respect to x, really this is the only change. The x to the power of 3n will go up by 1. This is now x to the power of 3n plus 1. We have to divide by the new exponent, 3n plus 1. And n factorial was already there to begin with. That's our full antiderivative. That's n antiderivative. There's still something missing. Anyone see what the missing portion is?
Plus c.
Yeah, so we still need our constant of integration. I'll put it to the left because I don't want it to feel like the c is tied into the series itself. It's that constant plus that entire power series. And although this problem didn't ask for it, it's an important side fact that the radius of convergence is still infinity, which implies immediately, if this is infinity, then the interval of convergence is from negative infinity to positive infinity as well. So now we can find power series representations of antiderivatives, where before we had to settle for the fundamental theorem of calculus. And even though this looks like a parlor trick, now we have an antiderivative. I don't know what the closed form formula is for that. In fact, none exists. At least we can do other interesting things with that thing. So this is something that would come up in a differential equations class, where we have to use power series, Taylor series, and Maclaurin series just to get our antiderivatives to solve our differential equations. But any questions with any of these things so far, folks? Okay, I think we might have to call class over a little bit earlier today, since these problems take a very, very long time. So if you have questions, I'm happy to stick around for office hours, do another problem if you'd like. If you need to get going, then that's completely okay as well. Next class, we're going to dedicate the entirety to just reviewing. And the problems that you'll see on the exam are going to be ones that look more like this, since these are the ones that we had a better chance to hit harder on the practice in class.